Hi guys, and welcome to this episode on dealing with imbalanced data. The objective for this episode is to apply various undersampling and oversampling techniques to an imbalanced dataset, which we discussed in the previous episode. We start off, as always, by importing our general libraries, so that is pandas to read our data frame, warnings to ignore warnings, and seaborn for any plots. In this case we don't use seaborn, so I'm going to remove this. We then filter any warnings. We can run this. So the main library that we use here is a library called Imbalanced to learn. And in order to use this library, you have to use specific versions of scikit-learn and imbalanced learn, sadly. And in this case, I'm using scikit-learn version 0.24 and imbalanced learn version 0.8. We start by reading our data frame in Python. In this case, it's a data frame that looks at predicting stroke. We then check the shape of our data frame. So we have 43,400 rows and 12 columns. We can check the column names and first few rows by using the head function. We then define our input and target variable. We do this for two cases. One for our complete dataset, and two for just our numerical dataset with missing values removed. The first case is for random undersampling and random oversampling, and the second case is for cluster centroids, atomic links, and SMOTE. So we can run this here. We check the distribution of our complete data target variable, and we can expect this to be imbalanced. So here we have 783 cases and 42,617 non-cases for our complete data, and for our numerical data with missing values removed, we have 28,524 non-cases and 548 cases. We move to our first method, that is random undersampling. We import the random undersampler from the imbalanced learn library. We initialize and fit it to our complete data, and lastly check the distribution of our target variable. So we see here that our non-cases has been reduced to 783. Same concept applies to cluster centroids undersampling. We import cluster centroids from the imbalanced learn library, initialize and fit it this time to our numerical data, and lastly check the distribution of our target variable. This one might take some time, since if you remember we are applying the k-means clustering algorithm and using the centroids as our undersamples. So here we have reduced our non-cases to 548, and remember that was the number of cases of our numerical distribution. We move to atomic links undersampling. Same concept applies as the cluster centroids undersampling, but this time we're importing atomic links from the imbalanced learn library and applying it to our data. Here we're only reducing our non-cases by 305, so this is only a small reduction and therefore might not be that useful for this particular dataset. We then move to our oversampling techniques. First, the random oversampler, and I forgot to mention that this takes the sampling strategy, which here we set to minority in order to oversample the minority class to match the majority class, and a similar concept applies for the random undersampler. So we can run this here. So here we have oversampled our minority class to match our majority class. Lastly, we apply synthetic minority oversampling technique to our numerical data. And this is quite quick to run. and here we have oversampled our minority class to match our majority class. Thank you very much for watching, and I hope you learned something new.